Hi, welcome to Modeling and Simulation of Dynamical Systems at Czech Technical University. In this video I would like to show you some rules how to design simple bond graphs. And we will proceed by means of a few examples. Let's start in electrical domain. We will consider this interconnection of a source of voltage, resistor, inductor and a capacitor. Their parameters are 0, R, L and C. And now the general procedure that I advise here is let's start by identifying the nodes. That means the places with distinguished voltage. In this particular case we can only identify 3 nodes and we will label them 0, 1 and G. G stands for the ground. The second step is to establish the coordinate system for both the relative voltages and the currents. This step is completely arbitrary, it's up to you how you do it, but once you do it, you need to stick to it. The third step is that we will start writing down type 0 junctions which correspond to the nodes, and it's recommendable to, while doing it, is to keep the layout of the original circuit. The fourth step is to use type 1 junction to include sources and voltage drops. In particular, in this particular case, we do it like this, while taking into consideration our coordinate systems in order to determine the directions of half arrows correctly. Note that these type 1 junctions, they always give you an access to the relative voltages. So we do it for all the 3 elements here, resistor, inductor and capacitor, and finally we'll also do the same for the source of voltage. And now we are done with drawing the bond graph, so the last step possibly is to simplify. In this particular case we can simplify by knowing that the voltage of the ground is set to 0, hence the power carried by all the bonds touching the ground is 0. Therefore, from the modeling perspective, there's no point in considering them. So let's see how the bond graph simplifies after eliminating those bonds that are touching the ground. Obviously, we can make one more simplification here. Whenever we have type 1 or type 0 junctions with just 2 bonds, we can eliminate them, provided the directions of half arrows is identical, which gives us the following resulting final bond graph. Voila, this is our first fair bond graph that we succeeded in constructing. Let's now jump into another physical domain, hydraulic domain. We will consider this interconnection of a motor and a pump which sucks water from some reservoir and then feeds the water further down into the pipe, to which there is a reservoir attached and some narrowing of the pipe, which constitutes resistance to the flow. The general procedure here is pretty much the same as in electrical circuits. That means we identify the spots of distinct pressure, we set the coordinate frame for the flows, and then we start by drawing type 0 junctions and then type 1 junctions, and finally we simplify. So let's have a look at how this will look concretely. So we augment our technical drawing with the distinct pressures, atmospheric, P1, P2 and P3, and we draw them at the beginning of drawing our bond graph. Then setting the coordinate frames for, and actually labeling the individual flows, Q1, Q2 into the reservoir and Q3 which goes on, and then using type 1 junction actually to introduce the model of the viscous drag and the inertia of the liquid, and similarly the model of the most probably nonlinear drag at the narrowing of the pipe, and finally using type 1 junction to introduce a model of the reservoir here of the capacitance. The last thing that remains is to bring in the power from the motor after transformation from the mechanical domain into a hydraulic domain. Here, unlike in the electrical case, we can't immediately discard the bonds associated with the atmospheric pressure unless we decide to use relative pressure instead of the absolute one. In that case, yes, we could cancel these 3 bonds and simplify. Finally, mechanical example, or an example in mechanical domain. We will consider 2 masses like this, interconnected with springs and dampers and attached to the external world. Now these are all in a gravitational field, therefore they feel their own weight. The masses are m1, m2, and the procedure here is different from what we did in electronic circuits and hydraulic systems. Here we start by identifying distinct velocities, and not only the velocities of the moving parts, but we will also include the label for the velocity of the reference frame, even though it's 0. The second step is, as usual, reference frame for the relative elements. The third term, type 1 junctions corresponding to the velocities, and the fourth step, type 0 junctions, which enable us to bring in the relative velocities. So let's start doing it. So we first start drawing the 3 type 1 junctions. I can immediately attach generalized inertances corresponding to masses m1, m2 to the moving parts. Similarly, I can also attach the sources of generalized effort here, which corresponds to the weight. And the same source, or actually the source of generalized flow, can be attached to the reference velocity, even though it's 0, so we will obviously cancel it out later. Still, I want to keep it there at the beginning. And finally, the relative velocities introduced by means of type 0 junctions. Now it may take a while to actually learn how to set the half arrows correctly here so that they are in agreement with your chosen reference frame. Certainly you want to have them in both directions because you always want to get the reference, the difference between the velocities. The last step that we can learn here is how to simplify this somewhat complicated bond graph, the one now in the red, in the yellow part. And the trick is here. So whenever we encounter interconnection on the left, we can rewrite it as the interconnection on the right, and I will just highlight the ones that correspond to each other.